Here's section 9.9, and in this section what we want to do, our objective, is to represent functions by a power series. And specifically the type of power series that we are going to be using is our geometric power series, which is nice because geometric is pretty darn easy. So we want to create a geometric power series. So we know that a geometric power series is, we have our summation from either n equals 0 or 1 or wherever we want to start to infinity. And then it would be a times that common ratio to the power of n. And we know that as long as the absolute value of our common ratio is less than 1, we know that it's going to converge. And or that we can even find the sum of it. And so if this happens, and if the common ratio, or that rate, is less than 1, then we can say that the sum of this series is equal to our first term, a sub 1, divided by 1 minus our common ratio. And so remember that that numerator, that a, whatever's in the numerator, and in this situation, because I said we're going to start at 0, anything to the power of 0 is going to give us 1 times a. So this numerator has to represent your first term. And then we know that in the denominator, it always is 1 minus then our common ratio. And so what we're going to do today is we're going to try to make things look like that common, or look like our fraction here. So a divided by 1 minus our common ratio. And from here, we're going to go do the opposite and actually write it as a summation with our geometric power series. So today the idea is to take this fraction and go back, write it as a geometric power series. So we want to make our functions resemble the geometric power series in all of this. Alright, so for example, this f of x, which is equal to 1 divided by 1 minus x, is really close to resembling a geometric series centered at 0. So if we look up here, yeah, it's really close to looking like this type of an idea, or this type of a fraction, and definitely centered at 0 because we just have x. It doesn't have to be centered at 0, and we'll look at that in the next example. But here it's centered at 0. It is really, really close to resembling a geometric power series. So we want to, first of all, let's write it as a geometric series, and then we're going to identify our interval of convergence. So when we look at our function, we have that 1 divided by 1 minus x. Now we have to think of the sum of a geometric power series, which we have above up here. And this is really nice because this one, obviously, first one, it's set up well for us. This number here has got to be a 1, and that's just part of our formula. So we know that that has to be 1. And that's in all cases that we have here, that this must be the number 1. Your operation has got to be subtracting. So this must be subtraction. And then that x is your rate. So this, in the denominator, you have to see the number 1. You have to have subtraction. Then you can have this x, and there can be a coefficient in front of here, and that's going to be pretty common. Then our numerator, this has to be our first term, and it definitely doesn't have to be the number 1. So knowing this, I can take the 1 divided by 1 minus x, and I can write it then as a geometric power series. So I'm always going to be starting at 0 and going to infinity. My first term is a 1, which we technically don't have to write in here. My common ratio, or rate, is x. That's to the power of n. So now I took this fraction, this f of x, and instead of having it as a fraction, we wrote it as a geometric power series. Now we can figure out, so we'll call that step 1 maybe, I guess. Now we have to look at identify our interval of convergence, so what we did back in section 8. With this interval of convergence, we always want to identify our center right away. We know in this situation our center is at 0. because this is obviously geometric, it's going to be really easy to figure out what your radius is going to be. And because it's geometric, we know that this x has to be less than 1. Same thing that we did in section 8. We can't split up our center. Well, great, we don't have to. There's no coefficient here. There's really no changing. So your radius is just 1. Therefore, our interval of convergence would go from -1 to a +1 if we're centered at 0. Slightly annoying, but it will be very easy. You do still have to check your endpoints. So we'll say, well, what happens if x is a -1? Then we have our summation, n equals 0 to infinity. We go back to our geometric series. So here's our geometric series. Wherever we have an x, we plug in a -1. And obviously in this situation, your rate is equal to -1. Therefore, it diverges. And basically, you're using geometric every time. So you don't have to say that you're using your geometric series with this. But diverges, it has a parenthesis. Check our right endpoint. If x is equal to a +1, summation, we'll start at 0, go to infinity, plug in a 1, 1 to the power of n. Again, our common ratio is equal to 1. Using our geometric series, we know that this is also going to diverge. So parenthesis. But the main thing here, the main idea, that new thing that we're doing is that we took a function, 1 divided by 1 minus x, and we wrote it as a geometric power series. Which I know to you is a pretty cool thing, that you're proud that you can do that. Oh, time to leave class, I guess. For B, now we take the exact same function, and so our function is 1 divided by 1 minus x, but now we want to say that the center is at x equals -1. And this is obviously going to affect this as we set this up. We want to write a geometric power series and again identify our interval of convergence. Well, what we have to do is take our original function. So we have our 1 divided by 1 minus x. We have to adjust for that center at x equals -1. Therefore, when I adjust for my center, I have to keep my two things equal here because I'm saying here is my function, they have to be equivalent. So I'm going to leave the 1 in the numerator, and I have 1 minus, but this x, if I'm centered at -1, that has to be x plus 1. Well, currently the two fractions that I have are not equal, and they have to be equal. So this is the original function. I have to stay equivalent to this. And basically right now, if I looked at the denominator and simplified it, and if I left it like this, I would have 1 divided by just -x. Well, 1 divided by -x is not equal to 1 divided by 1 minus x. So what we did here is we said, besides just the 1 minus x, we now have a -1. If we put a -1 into the denominator, we better offset that by putting in a +1. So we have now, if we look at everything, yeah, we have 1 minus x minus 1 plus 1. Great, we're back to our original function. So we have to take this and continue to alter it. So I have to keep my center here. Well, now I can say I have my 1 plus 1, which is going to give me 2 minus x plus 1 to the power of 1. But when I look back, I have to make sure, when I look back at this part, this has to be the number 1. This has to be subtracting. Your rate can be anything, and so that part of it is okay, but now if I look back here, that's definitely not the number 1. Well, to create the number 1, we have to divide all three parts by 2, or divide the denominator by 2, divide the numerator by 2. Doing that, it's obviously these things will stay equivalent, so now I have 1/2 in the numerator, divided by 2 divided by 2 is 1, minus, this is 1/2 x plus 1. And so now when I look at this, I have to have 1. I have to have minus. This is my common ratio, my common rate for a geometric power series. And that's okay that you have adjusted for your center and that you have a coefficient here. And now this will be my first term. So if I write this as a geometric power series, I have the summation. We're always going to start at 0 and go to infinity. It's our first term, 1/2, times our common ratio. So that would give us, instead of writing it as 1/2 times x plus 1, I'm going to put it as x plus 1 divided by 2. That's to the power of n. So I started off 1 divided by 1 minus x. We've altered our center, and if we look back over here now, we know that we are centered at -1. That comes from section 8. My first term I can identify right away, but here is our geometric power series. Now to identify our interval of convergence, which just basically goes back to section 8, and I'm going to call this part 1. So there's part 1. Part 2, identifying our interval of convergence. Looking at it, obviously our center is where x is equal to -1, and we have to calculate the radius. Well, we know that this is geometric, so the radius should be very easy to calculate. It's that common ratio, so the x plus 1 divided by 2 has to be less than 1. Multiply by 2, so I have x plus 1 is less than 2. And remember, you cannot split up that center. So that has to stay as x plus 1. Therefore, this over here tells me what my radius is going to be. The radius is 2. So if I'm centered at -1, I have a radius of 2. That tells me my interval of convergence would go from -3 to a +1. Now, annoyingly, yes, you have to test your endpoints to see if they converge or diverge. If x is equal to -3, alright, so we plug in -3 plus 1 is -2. -2 divided by 2 is a -1 to the power of n. Here, this is a geometric power series. So geometric, our common ratio is -1, therefore it will diverge. And we get a parenthesis. Check your right endpoint. If x is equal to a +1, we have our summation from 0 to infinity, 1/2. Plug in a +1, 1 plus 1 is going to give us 2. 2 divided by 2 is going to give us 1, which these values should always be -1 and 1. Because we're going right to the very end. And so, like that end point, if it were greater than 1, then it's not going to converge. So we want it to stop, and you should get 1 there for all of these. Again, this is geometric. Our common ratio is equal to 1, therefore diverges, which gets a parenthesis. So our two answers are geometric power series. That was for the first part of it. Our interval of convergence is from -3 to a +1. So my guidelines, what I'd say for creating a geometric power series, the first thing, always adjust for the center first, because adjusting for the center is going to make you probably add or subtract something into the denominator, and you don't want to do all this other adjusting and then be like, okay, well now I have to add something. Well, you always have to offset that. So number 1, adjust for that center first thing. After you've adjusted for the center, make sure that your fractions are staying equivalent when you do that. Then the denominator has specifically got to be 1 minus then that common ratio. So then that has to happen. After that, you can identify your first term, which is in your numerator. You can identify your rate, which is like the right side, I guess, of the denominator. And then write your geometric power series. So keep in mind, like, first of all, adjust for the center, then make the denominator 1 minus that common ratio there. Okay, a couple more examples, and things will get kind of weird if you look at the next page even. I call them bizarre examples because there are some bizarre things I like to do with this. So number 10, we want to find a power series for this function. H of x is equal to 1 divided by the 2x minus 5. centered at 0, and then again find our interval of convergence. So we have our two parts here. Number 1, set up our power series, which is always going to end up being a geometric power series. Number 2, test for our interval of convergence. Alright, so as we do this, I have to remember that everything has to stay equivalent to this original fraction. So I have 1 divided by the 2x minus 5. Usually what I like to do is put the negative 5 first, because and then that x will be the variable. That will always be my common ratio. So I have plus the 2x. This one is actually really nice because you're centered at 0. So this is definitely centered at 0. I don't have in parentheses x plus or minus something. We're already centered at 0. And that makes it really convenient and really nice. So, okay, great. I have the center part done. And it's okay to have a coefficient in front of that x. It's very common. You will probably most of the time. The next thing is that this has to be the number 1. So if this has to be the number 1, I have to divide the numerator and the denominator by negative 5. Doing that creates negative 1/5 in the numerator, and the denominator is 1. And this is nice because it creates subtraction. So I have a positive divided by a negative, and that would be 2/5 x. So that didn't take too much work in order to do that one. And write it as our geometric power series now. This is equivalent to the summation. Geometric will always start at 0, so n equals 0 to infinity. Our first term is the negative 1/5 from the numerator times our common ratio. Remember, this has to be subtraction, so our common ratio now is 2/5 x. That's to the power of n. And there's our geometric power series. Number 2, or the second part, to identify our interval of convergence. Well, we know with this one we're centered at 0, or where x is equal to 0. It's geometric. So when we have to find our radius, we say, well, that common ratio, the 2/5 x, has to be less than 1. We're centered at 0, so I just have to get x by itself. Therefore, x is less than 5/2. So for our common, or if our center is at 0, and our radius is 5/2, our interval of convergence would be from negative 5/2 to a positive 5/2. And yes, we get to test everything. So x is equal to the negative 5/2. Plug it into your geometric power series. So I have negative 1/5. If I plug in the negative 5/2 in for x, so if x is negative 5/2, that's obviously going to give me negative 1 to the power of n. And like I said in the last example, that common ratio, once you plug things in, should always be 1 or negative 1. So here we say this is geometric. Common ratio is equal to negative 1. Therefore, diverges. And they better diverge. If x is equal to the positive 5/2, summation from 0 to infinity, negative 1/5, plug in 5/2, 2/5 times 5/2 will give us 1 to the power of n. Believe it or not, this is geometric. Common ratio is equal to a positive 1, therefore diverges. We have a parenthesis. So our two answers, here is our geometric power series. Here is our interval of convergence. Moving on to the next one. And I like star this one. You better know how to do this type of a problem. This is about as tough as I can make it. And so you'll probably see one like this on your quiz and test. We have find our geometric power series. Power series are going to be geometric. For our function, f of x equals 4 divided by the 3x plus 2. We're centered at 2. That's step number 1. Then number 2, we have to calculate our interval of convergence, or find that. So obviously a little bit different here because we're not centered at 0, we're centered at 2. And that, when you're not centered at 0, it does make a little bit more work. So take our original function, and everything has to be equivalent to this function since we're writing a power series for this function. Again, we're going to set it up so it looks geometric. So I'm going to keep the 4. I'm going to keep the 2. But I like to put that first. I want the x second. So it's plus. And instead of writing a 3x, if I were centered at 0, I would definitely leave it like that. But I'm centered at 2. So if I'm centered at 2, it can only be x minus 2. You can't have a 3x minus 2. That doesn't identify the center. It can only be as a binomial in parentheses, x plus or minus a number. So since we're centered at that positive 2, it has to be x minus 2. So that 3 you have to factor out. So technically right now, if these things are going to be equal, I have a 3x, but I put in here a negative 6. I can't just put in negative 6 into the denominator and think that the two fractions are equal to each other. So if I do put in a negative 6, I better offset that by adding 6. And you obviously now you have 2 plus 3x minus 6 plus 6. Great, we're equal to our original. But that first thing you have to do, like I say in the guidelines on the previous pages, you, number 1, have to adjust for your center. So now we have 4. Put your like terms together. So there's your 8 plus 3 times x minus 2. Now we've adjusted for the center, and we've adjusted that value here. Remember, this number has to be a 1. So if it has to be 1, I better divide everything by 8. Therefore, in the numerator we have 1/2 divided by 8 is 1 plus 3/8 times x minus 2. Well, this looks pretty darn good right now, but remember our operation we have to be subtracting. So instead of 1 plus 3/8, we cannot have that be plus. It absolutely has to be minus. And I guess you could erase it and say minus a negative. I'm just going to write out the next step. So I have 1/2 divided by 1 minus, it's a negative 3/8 times x minus 2. So you have to make sure that you adjust for that. But then I've created this fraction now that looks geometric. My first term is in the numerator divided by 1 minus, here is my common ratio. So if I write my power series, which is specifically, we're always creating geometric power series, summation n equals 0 to infinity. Our first term is a positive 1/2, and our common ratio, negative 3/8 times x minus 2. All of that is raised to the power of n. There is our first answer. We have written this as a power series, and every time they say write it as a power series, obviously this is going to be geometric. Alright, the second half of this tells us find our interval of convergence. Well, we know now we are centered at 2, which it tells us in the directions, but even looking at this from what we did in section 8, we know that we're centered at 2. And we have to find our radius. Well, our radius, maybe now you can catch on pretty quick. You could say it's the x minus 2 times negative 3/8. That has to be less than 1. Remember, this is absolute value, so that technically becomes positive because a radius can't be negative. X minus 2, you cannot split up that center. Has to be less than 8/3. So kind of an ugly one. We like integers much better. But we have a radius at 8/3. Alright, test our interval of convergence. If we're at 2 for our center, subtract 8/3, and your left side should be negative 2/3. If you add 8/3, that should give you 14/3. And we get to check them. So what happens if x is equal to negative 2/3? We have our summation. N equals 0 to infinity. Remember, we're always going back to this thing. 1/2. if I take negative 2/3 minus 2, that is going to give me a negative 8/3 times negative 3/8. That should give me a positive 1. That's to the power of n. Weird, this is geometric. Common ratio is equal to 1. Therefore, negative 2/3 diverges. If x is equal to 14/3, summation 0 to infinity, 1/2. 14/3 minus 2 is going to give us 8/3 times a negative 3/8 is going to give us a negative 1 to the power of n. This again, believe it or not, geometric. Our common ratio is negative 1. Therefore diverges. And we have found our interval of convergence. Alright. And 12 is a pretty good example of what you're going to see on your quiz. I like that one. It's a good problem. Operations with power series. Moving on here. All of these things that I have written down are centered at 0. You definitely don't need to be centered at 0, but for the sake of writing it less, I guess I have everything centered at 0 here. So we have 3 operations that we're looking at. If you take your function, so this f of k times x, that's going to be dealing just specifically with this. What you can do is within your summation, the a sub n stays. In place of x, well, in place of x, it's going to become k times x. That's to the power of n. And this allows us to write this as a summation. It's a sub n times k to the power of n times x to the power of n. So if k is just a constant here, great, that's just going to change this number. You still will have x to the power of n, which should appear geometric with this one. For b, if I'm going to plug in, instead of just x, like here for f of x, I want f of x to the power of n. Same situation. We have our summation, it's a sub n. In place of x, this tells me it's x to the power of n, to the power of n. And now we know that power to a power, we know that we multiply. It's summation of a sub n times x to the power of n times n. But the nice thing is we'll use that idea that, okay, I have this one, I know something easy. Well, now I just want to make it maybe x squared. Great, in place of x, you can just replace an x squared. And that's what we'll be doing in the next examples. And then we'll also be doing this idea quite a bit if I want to add 2 series together. So we have the summation of a sub n times x to the power of n, plus or minus, it doesn't matter, summation of b sub n times x to the power of n. Well, you have that x to the power of n as your common ratio basically between these two things. You can put these two summations together, and so you have that common term x to the power of n, and then you can factor out basically, or you're factoring it out and you're left with your a sub n plus or minus b sub n. So if you have a common factor, which you're going to be looking for, we can take 2 and we'll be adding 2 series together. Well, if I have that common factor, great, I can factor it out to make it look a little bit nicer. A key thing here, when you apply these 3 operations, your operations will change your interval of convergence. I shouldn't say they will, but they definitely can. These can change the entire interval. Unlike what we did in section, I think it was 8, if we integrated or took the derivative, the interval could not change, but the endpoints could. These operations change your interval of convergence. The interval has to be the intersection of the intervals of convergence of the 2 original series. So, for example, let's say we have one series and our interval of convergence is from -2 to 1. -2 is included, 1 is not included. And we have another series, and we have our interval of convergence for that series maybe is from -1 to a +1. Well, you have to figure out between these two what is shared. Well, -1 would work. This is from -2 to 1. Here is -1 is my lowest one, but it doesn't even work. I can't use it. So if I combine these two things, -1 would be my left side. Here I have a 1 that's not included. Here the 1 is included. You have to find the intersection. So it would be 1 that is not included, because this one has to work for both of them. So the intersection of whatever, all the possible things that would work between the two. All right. So that's those operations are going to be used for these bizarre examples. And that's what I like to call them, because they are just a little bit bizarre. We want to find a power series centered at 0, and our function is 3x minus 1 divided by by x squared minus 1. And we want to find our interval of convergence. Well, when we do this, we have to make this look like our geometric power series. And our geometric power series does not have multiple terms in the numerator. It doesn't even have an x in the numerator. And it doesn't have an x squared in the denominator. So for this particular problem, we want to use our partial fractions, which you did in chapter 8. So partial fractions. And so instead of dealing with one of these things, or one fraction, which we just can't make it look like our power series very easily, we want to write this as partial fractions, meaning that decomposing of it, break it down and make them smaller fractions, because that's a lot easier. So remember, back to partial fractions, we said, all right, we have to completely factor our denominator. So if we do that, that gives us x plus 1 times x minus 1. These are linear factors, and so to create a proper fraction, your numerator has to be 1 degree less, which would make it a and b. Well, now we have to figure out what are a and b going to be, that if I add these two fractions together, I end up with 3x minus 1. Well, a we're going to have to multiply by x minus 1. B we're going to have to multiply by x plus 1. So the 3x minus 1, that numerator that we have to get to, is equivalent to ax minus a plus bx plus b. And then we look at our coefficients. So in front of the x we have a 3. And in front of our x's we'd have an a plus b. Our constant, we have a -1. A and b don't have variables with them, so those are constants, so there's -a plus b. This works out really well because I have an a and a -a, so I can add these two things together. 3 plus a -1 is 2. A plus -a is 0. B plus b is going to give me 2b. Therefore, b is equal to 1, and then a would have to equal 2. So, this original fraction, the 3x minus 1 divided by x squared minus 1, is equal to, a is 2, divided by, I'm going to set this thing up now, because it looks really good to be geometric. It's really, really close. Especially because here, if I look back, I'm centered at 0, which is a key thing and nice for these longer problems. And so instead of writing it as x plus 1, I'm just going to switch the order and write it as 1. And I don't want plus x because I know that I have to have minus. So it's going to be 1 minus a -x. So great. If a is 2 and b is 1, now this looks geometric. I have to add to it. Here my b is a 1. This one's going to take a little bit more work because we have to make that, has to stay a -1 plus x. I know that that value here, this number, has to be a positive one, so I better divide everything by -1. And then we have 2 divided by 1 minus -x. The numerator, I'm going to say minus instead of plus because that will make that a negative. And then here you get your 1 minus x. Alright, so now we're going to create two geometric power series, obviously one for each of our fractions. The first one, summation from 0 to infinity. Our first term is a 2. Our common ratio is negative x to the power of n. We're going to subtract the second fraction. We have our summation from 0 to infinity. Our first term is a 1. I'm not even going to put that in there. Our common ratio is x to the power of n. So we have two of them. We do want to combine these two things and write it as 1 because it started off as one fraction. And you really are looking for a common ratio or something common between these two things. They are going to be a geometric, so they always start at 0. They'll always go to infinity. But what we want to do in this situation when you have a negative x to the power of n, and that's going to be pretty common, is that we're going to rewrite that summation. So it's still 0 to infinity. We have our 2. We can factor out a negative 1 to the power of n, and then it would be times x to the power of n. Because this is technically, instead of just negative x, it's negative 1 times x. I can take the exponent to both of them. Minus our summation, n equals 0 to infinity, and then obviously x to the power of n. So what I can do is I can combine these two things. I know that I have that common ratio, that common term, I guess, of x to the power of n. So n equals 0 to infinity. I have x to the power of n. And now what do I have to do to get back to this first term? It's 2 times negative 1 to the power of n. To get back to this, I just have to hold its place, so it would be minus 1. But now, this is a pretty ugly looking thing. It's not that obvious geometric like it was before because you have this subtraction. So geometric, you just have that a times x to the power of n, and now granted this is some a, but it's pretty ugly. But here's what I'd be looking for. There's your geometric power series. We also have to find our interval of convergence. Well, because this is no longer geometric, this is pretty ugly to go back and try to find our interval of convergence for. So what we're going to do, and if we look back here, is your interval will have to be the intersection of the intervals of convergence from your two original series. Well, the original series were really easy to tell. So if I look at these two original problems, and I just say, hey, what's my interval of convergence for these two things? For both of them, you know that you're centered at 0. You also know that your radius is equal to 1 because it's geometric, and you know your interval of convergence is from negative 1 to a positive 1. Exact same thing for this one. So my center is at 0. My radius is equal to a positive 1. And then we have from negative 1 to positive 1. So this interval of convergence, once we combine them, because they're the exact same, that's a pretty easy one. Interval of convergence, negative 1 to positive 1. Alright, so keep in mind that partial fractions, when you have two parts to it and it's just ugly looking and the denominator looks quadratic, we can create linear factors and much easier. So kind of a bizarre example, but that partial fractions, when you get to something like that, make sure that you're ready for it. And really it's just kind of double the work. So in one problem I can make you do two things. So I kind of like that too. To get a little bit more bizarre on you here, we want to find a power series that represents natural log of x. And we want this to be centered at 1. Why we want it centered at 1 instead of 0 is because we know 0 is not included in the domain of natural log. So this looks really ugly because so far we haven't dealt with natural log of x at all in this section. Everything's been a fraction. We've said, well, we'll take that fraction and make it look like the sum of a geometric series. And so it's our first term divided by 1 minus our common ratio. So we have to try to make this natural log of x look like the fraction. And in order to do that, and this is why it's bizarre, and I don't know if I would have came up with this right away on my own right to start with, but I know that the derivative of my function So the derivative of natural log x is 1 divided by x. At least now I have a fraction to get started with. But we have to remember that as I go through this, I'm writing a power series for the derivative. I'll have to go back and write a power series for the original function when I'm done. So here's for the derivative. I have to have this centered at 1. Alright, well if I have to have it centered at 1, I always put it in parentheses. I need an x minus 1, and I'll put it over on this side. Obviously these two things aren't the same because I just randomly put in a negative 1, which I can't do. So I'd have to add 1 to the denominator. Well, now I know that these two things are still equal. And then it's close to being geometric now. We just need it to be 1 minus the negative x minus 1. Ooh. So, writing this thing as a as a power series, n equals 0 to infinity. My first term is 1. Great. My common ratio, negative x minus 1. That's to the power of n. What we want to do in quite a few of these situations, if you have a negative here, we can rewrite this. So it's our summation 0 to infinity. We want to write it as negative 1 to the power of n times the x minus 1 to the power of n. And that's going to be a pretty common thing that we want to do. What else, looking at this thing, yeah, I guess that's good. From here, this is our derivative, and we want to write for our original function. So if you have your derivative and you have to get to your original function, remember we have to integrate. So if we integrate the derivative, that would create our original function. So if we integrate this, it's just the power rule, what we did at the end of section 8. And then you have your summation, 0 to infinity. The negative 1 to the power of n is just going to stay, because that's just an alternating number. But then your power rule is x minus 1, that's to the power of n plus 1. That is all divided by n plus 1. Kind of weird about this situation. What we have to be careful about is where we're actually going to start this thing. And so here, if I say that n is equal to 0, when I look at that, if I plug in a 0, okay, the denominator, whatever, is fine. But if I plug a 0 into the numerator, my first term is x minus 1. That would be to the power of 1, so it would be x minus 1. When we actually want our first term to be, I think we should want it to be 1 over x. For some reason, I think that this thing should change and be where n is equal to 1 to start for our power series here. And I gotta think about why that happens. You could write out, which is really annoying, you could write out some of our terms that we did back with our Taylor and Maclaurin series. We could write out our terms and figure out, okay, which one has to be which, and that's probably the easiest way to do this. Is to say, all right, well, if I have to represent natural log of x, if we're centered at 1, I think our first term, f of x, is equal to x minus 1, and then it was positive or negative, I can't remember, x minus 1 squared divided by 2. So if we go through and check this, then we would have to figure out which term actually works. And I know that here it would be where n is equal to 1 to start. So I'm not going to do anything real crazy with that on tests or quizzes, but you'll have that situation where if you check your answer, that might be kind of weird there. Alright, so not a great answer for that, but I hope that it makes sense. You'd have to write out your polynomial and figure out where it's going to change. There probably could be a shorter way to do it, but I think that's probably the best guarantee that if you should change it from 0 to 1. Last bizarre example here is that we want to find a power series for arctangent x and centered at 0. So a pretty similar situation to what we just dealt with natural log. Arctangent of x is obviously not a fraction, and we want to deal with fractions. And to get a fraction, we can get one by taking the derivative. So we can say g prime of x. Remember, the derivative of arctangent is u prime, which would give us 1, divided by 1 plus our u value squared. So this looks pretty good, because at least we have a fraction, but we don't like having that x squared. And really, you can't even use partial fractions because you can't factor this thing. So what makes this a little bit more unique and weird is that we do know, I'm going to call my new function f of x. We do know how to write 1 divided by 1 plus x as a power series. And so in this situation, if I write this as a geometric power series, it would be my summation from 0 to infinity. My first term is 1. I would have to make this a negative x to the power of n. And instead of writing a negative x, just get used to saying it's negative 1 to the power of n times x to the power of n. So we do know this part of it. Now, if we apply our properties and say, well, I just want, instead of having just an x, I want my x to be x squared. So apply properties here. We can just say, well, I want x squared because that's just going to square this, which takes us back to what we have here. So if we apply properties, g prime of x, yeah, I don't know if I want to call it g prime. Yeah, I do. G prime of x, sorry, is going to equal the summation from n equals 0 to infinity. I want to take my x and square it, so in here I just want to take my x and square it. So that allows me to have negative 1 to the power of n times x squared to the power of n. And I'm going to go way back up to show where this is. It's applying this property as I went through here. So instead of just having an x, I want an x to the power of n. Great, I can just make it x to the power of n. Alright, so looking back at this now, we know that here is the derivative of the power series that I want. I want just g of x, so I need to integrate. Because g of x is equal to arctangent, which I'm trying to write a power series for. I have my summation from 0 to infinity. The negative 1 is not going to matter. This technically is x to the power of 2n. So that would give me x to the power of 2n plus 1 divided by 2n plus 1. Oops, and then because I'm integrating, I have to add c. I don't think I did that on the other one. So you only add 1 to the exponent. You're not adding 1 to the n. So over here, only add 1 to the exponent. It is not specifically n plus 1, because your power rule just says take your current exponent, add 1 to it, and then divide by that new exponent. And so when I say it is not the n plus 1, because if you left the 2 in there, it would end up being this, so then it would look like 2n plus 2, and it should not be that. So, bizarre, couple of bizarre examples, but you know that they're going to be bizarre when they're not a fraction to start. And so usually the derivative of the function that I give you is going to be a fraction. And you've looked at most of them then. So arctangent creates that derivative is a fraction. Natural log, that derivative is a fraction. And you have to create that fraction specifically so that you can make a geometric power series out of it. The homework for this section, there's not too many of them. So I think that this one you should get as much done as you can for tomorrow. And most of them are pretty easy. There aren't too many of the bizarre, crazy, weird things that are going to happen. So number 1, adjust for the center right away. Then when you adjust for the center, make sure whatever you add to the denominator or subtract to the denominator, you better offset that. And then also, that denominator has to be 1 minus. And the common ratio can be really anything. And your first term, it's going to be a constant, but it can be any fraction there or integer. All right. Have a great day.